Right, tonight's lecture is on the Grade 2-star listed Crystal Palace subway. Constructed in 1865, it is the most substantial remaining part of the huge Crystal Palace complex. So tonight we've got Historic England architect Ian Harper, Thompson Ford architect, Clive England, and Cristian Petrescu from the Morton Partnership, structural engineer. I think Ian's going to go first. Thanks.
Good evening, and thank you, Kim, for that invitation to speak here tonight. We will be hoping that there will be a seamless transition from one to the other, as the three of us. I'll be speaking briefly about the history of the site, about its condition, and about Historic England's role through grants and statutory provisions in its repair and restoration, all tinged with a few technical observations. Firstly, some notes on the history of the site. And instructed by Prince Albert, the Crystal Palace was first built in Hyde Park for the 1851 Great Exhibition. It was designed by Joseph Paxton with support from structural engineer Charles Fox, and it took 9 months to build. That's not the Hyde Park one, this is coming, this one. Using prefabricated cast iron and glass components. It was half a kilometre long and over 100 metres wide. By 1854, it had been rebuilt on an even larger scale at Sydenham Hill in South London, now known as Crystal Palace. It formed the centrepiece of a landscaped park with massive terraces, fountains, and a series of lakes, and of course the famous collection of extinct animals commonly referred to as the dinosaurs. Twin pagoda-style towers, and I think you can just see them there, one on the left disappearing and one on the right-hand end, designed by Brunel, supported the water tanks which drove the fountains. From 1865, first-class passengers from Waterloo and Victoria arrived at the newly opened high-level station, designed by Charles Barry Jr. The subway was built to provide access under the Parade Road, which runs along the top of that diagrammatic map there, to provide access directly into the palace via a ticketing hall and grand staircases. And it seems that we've not been able to find any original drawings for the subway. And I read recently somewhere, but I lost the reference, that there had been a fire in Barry's office a few years after this was completed, which destroyed the drawings archive. So there's a certain amount of logic there. The station and the subway were closed during the First World War for the war effort, and again for the Second World War, in the Second World War, after local bombing had damaged the railway tracks leading to the station. Although the subway was used as a bomb shelter during the war, and incidentally, evidence of this function has been preserved in the form of a urinal trough in the floor. This is there for all to see now. In November 1936, the palace burnt down, fueled by heavy teak-boarded floors, and the spectacular fire was seen from across London, even by my mother as a child living in Highbury. By 1954, the station was closed, and it was then demolished in 1961 to provide land for housing. The vestibule, of which this is a view across here, having lost the glass from its roof, fell into disrepair. After removal of the roof structure for safety reasons, the wall tops decayed and the north wall developed its bow and its lean, which led eventually to it being taken down and rebuilt. And trees grew out of the masonry. These two pictures show the view across the vestibule, I've always referred it to as a ticketing hall. It doesn't matter what we call it. It was the sunken courtyard where people bought their tickets and went up the staircases into the palace. By the 1990s, National Highways responsible for the Parade Road, that's the A214 Trunk Road, were concerned about the effects of water penetration through the road and the effect this might have on the load-bearing capacity of the brick vaults. And here we've got one view looking to one side, that's the north wall, the one that's leaning before being attended to, and the other picture on the right is looking back towards the park, towards the beginning of the staircases that led up straight directly into the palace. In July 2001, Bourne Consultants reported on 3 trial excavations in the western pavement to ascertain the nature of the construction above the vaults and the presence of services. It was established the upper side of the brick arches was topped with a layer of pitch or bitumen, with possibly a layer of puddle clay above the pitch. It's very important for what happened later on to realize that there was knowledge already about the original construction, but it wasn't always taken notice of. And here we've got a few pictures showing the other view. That's the view west through the vaults themselves, and the wall above there is the wall of the Parade Road, and the other picture on the left is the south elevation. So the open arches of the 3 on each side, north and south, led to what we call the lower staircases, north and south. There were 4 staircases altogether. Subway comprises various elements: the West Terrace, owned by London Borough of Southwark, the vaulted subway, the vestibule, and the 4 staircases. It is a listed building, raised to Grade 2 star in 2018, following Historic England's recommendation to DCMS. It lies in a Grade 2 star registered park and garden. Now, we call it a park and garden, but that's the whole of the Crystal Palace Park, basically. The subway has been on the Historic England Heritage at Risk Register since 1990. Principal concerns were to do with waterproofing of the vaults and the stability of the bowing north wall, already mentioned. So in 2014, Donald Insel Associates were appointed by London Borough of Bromley to carry out a survey of condition, an options appraisal, and a conservation management plan funded by a development grant from Historic England. The investigations included the drilling of trial holes and opening up of the subway walls to determine the nature of said construction. And the report considered all options from full restoration to preservation as a ruin. In August 2019, London Borough of Bromley was awarded £2.3 million by the City of London SIP Fund, SIP being Strategic Investment Programme, for the restoration of the subway. Historic England offered £500,000 to make up a shortfall in the costs. Thomas Ford and Partners were the successful tenderers for the full package of consultancy services. Tendering of the repair project resulted in 2 value engineering exercises, and as a result, the waterproofing of the Parade Road was deferred to a second phase of works. Historic England continued to support the repair project with further grants, the total expenditure in excess of £1.2 million. And Historic England's new chairman, Lord Mendoza, officially opened the subway on 17th of September last year, 2024. Couple of details of the brickwork. On the left, left and middle existing condition, and on the right, the result of repairing of the middle condition situation. You can see the large cracks. This is standing in the opening through the north wall and looking west, and the cracks reflect the movement of that wall outwards. And I've already referred to it being heavily bowed right along its length and also leaning into the vestibule. On support and governance, the site was occasionally opened to the public by the Friends of the Crystal Palace subway. Local interest in the subway has grown from the 1990s onwards and has gathered pace for the last 15 years. In 2011, a Crystal Palace Park community stakeholders group published a mission statement for the governance of the whole park. In 2014, the National Lottery funded a research project by the Friends of the Subway. This included archive research, historic interviews, arts workshops, and film screenings. Tour guides were trained, and 750 visitors guided through the subway at their open house day in September of that year. A year later, the first proposals were published for the establishment of the Crystal Palace Park Trust, and this was finally established in 2023. Following completion of the project, the Friends of the Subway stepped down from their formal position to concentrate on other projects. They felt their work over 25 years was complete. The London Borough of Bromley handed over maintenance and management to the newly formed Crystal Palace Park Trust. On technical advice, I think a couple of pictures of the vaults and showing on the left-hand side pockets of deteriorated soft red brickwork due to salts evaporating from the leaks coming through over the years, and on the right-hand side, stainings from leaks. This is the investigation through the pavements conducted by AECOM for London Borough of Bromley to establish the construction of the vaults. And we're right on the west parapet of the Parade Road. That's on the station side here, where by digging down through the pavement, you come onto the vaults as they came up to the terrace supporting wall. As the London region architect, I've been able to input advice from the early stages of the project. We advised the London Borough of Bromley's Highways Department on options for weatherproofing the vaults. A trial was carried out in 2017 to waterproof the vaults from below using injected resins. This was not successful, and the conclusion was that the vaults would have to be waterproofed from above. We haven't quite caught up with the pictures there. So there you can see detail of the soft red bricks destroying themselves with the salts evaporating from the water coming through from the road above. As part of our conditions for grant, we included the need for a brick consultant, and David Pope was appointed to the team. We included the request for dampness surveys so that changes in environment could be assessed. Through our National Technical Services team, we have had advice from civil engineer Alistair Massey. It's nice to see you here tonight, Alistair. And he's been instrumental in reviewing the strategic drainage design as well as detailed design behind the retaining walls. It became apparent during the appointment of the professional team that there would not be time within the tight SIP-funded programme for the preferred two-stage development and repair project. It was inevitable that unknowns would be discovered during the contract and that there would be cost and time implications. Clive and Cristian will explain the implications of this. And just to finish, And one slide, works in progress, but there's a lot more of that to come. And some ironwork relics that are still available to be seen on the Crystal Palace Park site. Railings, a boundary marker, and a rebuilt section of the metalwork of the lower part of the palace itself. Just to emphasize the presentation materials which were prepared by the contractor in preparation for several public open days, which were built into the contract. And finally, lettering for the date plaques, which is the last thing to be put up before the opening. I think they just got there in time, and done by a local letterer, George Edwards. Thank you very much. Is it all joined up? No. Okay.
So thank you, Ian, for the introduction, and thank you also for all your help and support and guidance throughout the project, which has occupied the last 5 years as of very shortly of our collective lives. So I'm and because it all took so long, it's impossible to encapsulate a fraction of what went on, what we found out, and some of the problems that we encountered. But I will try and give an overview before letting Cristian talk to you about the structural engineering. So, as Ian mentioned, we were appointed to lead a multidisciplinary design team, 10 consultants, including ourselves, and that was in April 2020. The brief was based on the INSAL's report and feasibility study, and that was what we were tasked to take forward. So, first of all, a little bit more historical context. You can see in this drawing the high-level station with the Crystal Palace behind it. The subway is indicated by the red arrow. So paradoxically, although it's a subway, it was actually accessed at first floor level from the station, which is a strange thought. And in an aerial view here, it's a very small building between two gigantic buildings. And it has to be, in its time, it was simply a route from one to the other. So people would arrive at the station and rush through the turnstiles to get to the Crystal Palace and all its glories. Unfortunately, without stopping to take photographs or record their impressions, the lack of photographs was something that came back to trouble us when we were researching the repairs. And finally, just because we haven't had one, here is a photograph of the Crystal Palace burning down. but the subway survived, but only just. The fire burnt itself out against the doors of the subway on the east side, and there's still traces of that fire damage there to this day, burnt into the paving and also the remnants of the sliding doors. And as Ian said, the subway was left in an increasingly derelict state. So following our appointment, we commenced work with the detailed surveys of the structure and fabric that we all carry out on these projects. And these are the condition survey drawings marked up to show areas of damage, areas that were missing. And then for the contract stage, there were drawings showing areas also for reconstruction. This is the survey drawing showing the paving in the vaulted area. So we developed the vaulted area as part of the contract documents, even though ultimately the work didn't take place. So we were unable to undertake any intrusive surveys during the pre-contact stage, which was unusual but understandable because of the funding arrangements, but it did leave a number of unknowns that we would have preferred to have cleared up in advance. So the work's in progress, but what I want to say in this section is just that the project, oh dear, too sensitive. The project initially included the whole of the subway, both the east courtyard and the vaulted area. Was a full restoration of the brickwork in both, a new roof to the east courtyard, and also a new power and lighting throughout. The project overlapped with the pandemic, of course, which was certainly one of the contributory factors to the high tenders that were received. And that resulted in the scaling back of the project following a VE exercise. But so the project as completed included everything on the east side that was originally in the project, and nothing in the vaulted area except some minimal lighting and power to support the fire escape strategy. So I'm now going to talk about 4 areas of interest that relate to the project. Each of these could be talked about in a lot more detail, and there are other topics as well, but that would take the rest of the evening in all probability. The brickwork and stonework were a major part of the construction project, and I have to give credit to DBR for the high quality of workmanship that they achieved, which was one of the reasons that they were selected in the first place. The brickwork did present some challenges, though. The upper left picture, I'm sorry if I showed it, the upper left picture shows the Galt brickwork, which had these splendid vertical perforations, which provided both a perfect water trap and a route to frost damage, and you can see it blowing the face of the brickwork there. It also provided the unusually strong bedding mortar with an iron grip on the adjoining bricks, meaning that the projected recovery rate from salvage brickwork turned out to be less than anticipated and led during the contract to a need to source additional replacement bricks. The red bricks, at least those that we dismantled, appeared quite reasonable to an external inspection, but a lot of them had very little structural integrity, and these also came apart during dismantling. The upshot of this was that with Ian's agreement, it was decided that the north wall would be rebuilt entirely using new bricks rather than with some salvaged bricks, and that all the bricks that we were able to salvage were used for repairs elsewhere in the existing walls. But during the contract, we also had to source new bricks, which with the help of our brickwork consultant was accomplished very well, and we had a good match with those bricks. And also the cleaning trials resulted in the selection of a technique which restored the brickwork to a much better appearance than it had. You can see the condition of it after many years of water leaching through from behind. It was quite a poor sight. So I mentioned earlier about the lack of photographic records of the subway and the lack of drawings. So that in reconstructing some elements, we had to rely on really quite fragmentary evidence. This is an assemblage of some of the pieces of information that we had available to us for the sliding doors, which closed off the 4 staircases to the Crystal Palace from the East Courtyard. So on the left, there are the remains of one of the runners that carried the doors on an overhead rail. We found 1 or 2 fragments in the brick door pockets that the doors slid into when not in use, having escaped the fire, although still with charred wood attached to them. But these were quite small fragments. You can see in the upper left-hand photograph that's a photograph taken post-fire. So it had burnt right through the door, leaving some fragments. The other door had disappeared completely, and it had burned all the timber out of the headrail as well. It was a very, very intense fire. But between these and the blurry photographs that you can also see on this slide, we were able to piece together with a reasonable degree of accuracy the design of the doors. And I think with the exception of the exact profile of the panel moldings, those doors are a very close replica of what originally existed. The moldings are typical of the period moldings that Ian and I had a discussion about before arriving on a profile. These doors were no small piece of work. They're 3.5 meters tall, and the stiles are around 73 millimeters thick. They're enormously heavy, and but they really do finish the subway off, as well as providing some important security. So this is something I think that Cristian is going to talk about, but this is the architectural background to it, if you like. So the staircases are a rather curious arrangement. So I'll show you a drawing in a second and just explain about the upper and lower staircases. But essentially pre-contract, 3 of the staircases were visible. The 2 on the south were intact, and sorry, the 2 on the north were intact. And one of the stairs on the south, the lower stair, was visible and clearly missing quite a number of the treads. The upper south stair was completely buried, so we had no idea what might remain, but we had scheduled for a complete set of stone steps in the event that they were all missing. So although we couldn't see it, we did have some solid information, or so we thought, in the form of a 1964 LCC survey drawing, which you see here. And as I said, it says boldly in the job survey of EM Barry vaults, etc. And then on the left is the drawing. So you can see the 2 arrows. The reason that the plan of the stairs has been split is that the upper stairs sit directly above the lower stairs. So you couldn't actually represent them in a true plan form because you would only see one set. The one we're talking about is the one with the red arrow showing the connection. So imagine our surprise when DBR excavated the stairs and discovered not a straight stair, as the LCC had said, and as our drawing showed, but the landing of a dogleg stair in perfect condition and with its surrounding walls. And so this did create a number of problems and structural complexities, but there is a lesson there, which is don't rely on drawings that are labelled as record drawings unless you've done the recording yourself. So as a counter to what I just said earlier, the form of the original roof was actually quite well known. The structure survived until the 1950s, and it was a pair of pitch glass roofs running east-west, supported on corbels at the outer edges and columns in the centre. And even with the roof gone, the profile of the roof slopes was clear. So it would have been straightforward to recreate the just going to go back. It would have been straightforward to recreate that roof, but there were a couple of problems with that. The first was that the client felt that a clear interior was important for the future use of the subway, so which is something that the columns would have impacted. And the second was the valley gutter, which I felt was just a maintenance hazard. Things do get thrown over the wall from Crystal Palace Parade. It will be difficult to maintain, difficult to inspect. And finally, none of us could work out how it was drained or where it was drained to. And despite discovering a lot of other things about the drainage during the course of the project, including the original subfloor drains, what we do know is that it wasn't connected via the cast iron columns to that drainage. So with all of those factors taken into account, it was decided that the best thing was to look at a new design for a clear span. And we undertook a number of sketch designs, thinking quite freely, as we were encouraged to do. But in the end, the choice came back to something fairly traditional with a single span pitched roof. So this was an ongoing discussion involving ourselves, Cristian telling us what was feasible and what was not, and the client team. And so the end result was this design. This is what went in as part of the planning and LBC application. So it acknowledges the form of the original roof, but doesn't replicate it. And so that's there was also part of the planning application drawing. It gives you a good idea of the rather curious plan form of the subway and of the staircases, which originally, in a manner that is not entirely clear, emerged inside the Crystal Palace, or at least in a leans-to structure of some sort attached to the west side of the palace. But that was beyond the scope of this project. This is where we ended up. And with that, I'm going to hand over to Cristian.
Good evening, everyone. I must confess that I find it a bit difficult to come and talk right after Clive and Ian, who are not only extremely knowledgeable, but so natural when it comes to public speaking. I will do my best, though. Right, so let's start with a brief overview of what we will be talking about tonight. We will start with the site plan and key areas of structural work, diagnosis and possible underlying causes for the historic structural failure of the original fabric, the scope of work and initial structural proposals, project constraints and engineering challenges, sustainable development considerations, as-built structural proposals, and in the end, we will wrap up the presentation with a few conclusions and a very interesting short video by Historic England about the Crystal Palace subway project. Site plan and key areas of work. As a very short structural description, the subway itself comprises masonry fan vaults with columns assumed to be hollow and infilled, made of brickwork to the outside with compacted stone to the inside. The abutments are made of brick masonry walls, and as you can see on the key plan, the Crystal Palace Parade runs directly over the subway. The subway appears to be in reasonably good structural condition, and therefore no work has been undertaken in this area at this stage. As mentioned by Ian and Clive, I believe waterproofing works are envisioned to take place in the foreseeable future. The east courtyard, north and south retaining structures are made of masonry gravity walls and a brand new roof structure now spanning between the walls in question. Last but not least, the upper and lower staircases and associated retaining walls. I believe it was Albert Einstein who once said, if you want to know the future, look at the past. I believe this very much applies to structures as well. And for this reason, I think that as a start, it would be worth quickly touching base on the possible causes of the historic structural failures of the original fabric, as this helps us as a design team rectify some of the original weaknesses of the design. Starting with the east courtyard roof. As Clive already mentioned, we know from archive information that the east courtyard used to be covered by a cast iron glazed roof. Unfortunately, soon after World War II, the former ticketing hall and implicitly the roof fell into disuse, and later on, due to the roof's precarious condition, it was taken down. The east courtyard north and south retaining walls. To give you a bit of background information, these walls had been stabilized in 2018 by ECOM. 250 mil diameter bored micropiles were inserted into the ground at different angles with a pile length up to approximately 12 meters, connected at the top with a 750 mil deep RC pile cap. Now, going back to the original fabric, there are quite a few factors that we believe contributed to the historic structural movement of these walls. A few examples: blocked drainage behind the walls. Everyone here knows that it is good and common practice to incorporate drains behind retaining walls. These are, of course, not only designed to avoid water building up against the back of the wall, which inevitably will penetrate the wall and make it damp, but they also serve as a way to relieve the retaining wall of the hydrostatic pressure. When the retaining wall is 5 meters high in height, like the walls in question, an effective drainage system can lead to significant hydrostatic pressure. The second one, lack of maintenance. As we all know, Mother Nature has an incredible power of regeneration, and there are quite a few famous examples out there where nature has reclaimed its territory. See Chernobyl in Ukraine, the temple ruins of Angkor in Cambodia, Ciudad Perdida in Colombia, and the list goes on. This, of course, to a much lesser extent, was starting to occur at around the east courtyard of the Crystal Palace subway. Once the vegetation roots find their way into the fabric, they expand as they grow, inducing tensile stress into the brickwork, which leads to cracking and structural movement. Cracking will then create room for more roots to grow and expand, and thus the decay continues and accelerates. On the as-built drawing issued by ECOM in 2018 and the health and safety file of the micropiling works, there is evidence that above the north retaining wall and the northeast passage, there were at least 3 mature trees that were removed during these works. The reason I'm mentioning this is that this could potentially explain why the structural movement noted to the north retaining wall was found to be more severe compared to the one noted on the south wall. The third one, poor workmanship. The facing brick skin of the walls had been originally tied back to the retaining wall through the use of brick headers. As we all know, bricks are quite resilient to compression, but very weak in tension and even in shear when working as independent units. As structural movements started to occur for the reasons that I've just mentioned, many of these stretcher ties snapped, causing the brickwork facing skin to bulge out even more. This explains why when the external brick skin of the north wall was dismantled, we noted that the bulge in the load-bearing wall behind was less severe than in the facing skin. Last but not least, the collapse of the original roof, although not crucial, to some extent, the original roof likely provided lateral restraint at the top of the retaining walls. Today's lower and upper steps and associated retaining walls, the same assumptions apply in terms of possible reasons for the historic structural failure. You can see in the bottom picture of the slide the extent of the vegetation before this was finally removed. Again, the presumed original roofs over the lower and upper steps would have provided some sort of lateral restraint to the head of the walls. Scope of work and initial structural proposals. In 2020, we visited the site twice and updated our previous structural condition report. The second visit enabled us to get a better understanding of the level of decay and damage once the vegetation overgrowth was finally removed. Some of the urgent works we recommended then were treatment of the vegetation roots using approved biocides, local brick stitching and repairs to the brickwork damaged by vegetation overgrowth, local brick stitching and repairs to the brickwork, local brick strengthening where damage had occurred due to structural movement, and investigation of the water ingress source to the subway structure. The east courtyard roof. This is to give you an idea of how the structural scheme developed from the concept phase up to the construction stage. Two of the very first proposals for the new roof were to build glulam structures that would have spanned north to south and supported onto the 2018 pile capping slabs. Of course, in this situation, the span would have been larger than in the final proposal, namely approximately 18 meters compared to 15 meters, and most likely less cost efficient as well. I'll talk about the third and final proposal of the roof structure later on. The east courtyard north and south retaining walls. Given that the north retaining wall was bulging out excessively, we first looked at the worst case scenario option of carefully dismantling the wall and rebuilding it cost efficiently while keeping the original architectural appearance. Therefore, our initial proposal was to rebuild it in reinforced concrete and allow for the facing brick skin to be set on the structural base slab of the RC wall and tied back to the RC stem. As we wanted the RC wall to be as slender and lightweight as possible, the void to the back of the RC stem resulted from dismantling the thick brickwork was proposed to be backfilled with a lightweight granular material, which would have been both a free draining and sustainable solution. Furthermore, to provide lateral stability to the RC wall, its stem would have been tied back at the top to the existing RC pile cap at regular centers. The opposite wall to the south was leaning significantly less, and therefore only localized strengthening was deemed necessary. The east lower and upper steps and associated retaining walls. The southeast upper and lower steps were in very poor condition, as you could see in the previous slides from Ian's and Clive's presentations. And once the vegetation overgrowth was cleared, it was found that the west retaining wall was bulging out excessively and was beyond repair. To establish the most appropriate structural solutions, we started by identifying the likely underlying causes of the original wall's failures. Once we identified some of these and made initial assumptions to be confirmed during the site investigations, we made a list of different potential solutions with the advantages and disadvantages of using either of them. Having gone through each of these options, we decided to opt for the RC wall solution as the benefits of using this outweigh the disadvantages. Some of the main advantages of this option were the better spread of the load to the ground and the monolithic construction of the L-shaped retaining wall, providing both a structural base for the stone treads and retaining the soil behind, and also good durability versus construction cost ratio. As we will see shortly, ground anchors were required, and the design of these was done by others, as this is a specialist design where, of course, the input provided by a geotechnical engineer is crucial and outside the Morton Partnership's area of expertise. However, the ground anchors were designed based on the propping forces resulting from our RC wall design. Therefore, this required efficient coordination between the ground anchor designer and the Morton Partnership. Moving on to the project constraints and engineering challenges. Dealing with existing structures is always challenging due to the high number of unknowns. As any intrusive investigation needs to be kept to a minimum for conservation reasons, the design proposals always need to leave room for tweaks during the construction stage, ensuring that these changes can be accommodated relatively easily to mitigate the risk of causing delays to the overall construction program. Now, I'm sure most of you already know this, but when dealing with historic structures, the generally recommended approach within the conservation industry, broadly speaking, comprises 4 structural design phases, namely the first one, a structural survey, normally a visual inspection of the structure to identify any structural defects and their extent, which allows the structural engineer to familiarize themselves with the structure, its setting, etc. The second one, diagnosis. In this phase, using the information gathered during the damage survey and through a series of further desktop and site investigations when applicable, such as historic building assessment, GPR survey, arboricultural survey, intrusive investigations like opening ups, trial pits, geotechnical investigations, and so on. Based on these, the structural engineer identifies the underlying causes of damage and decay. The third one, structural assessment, through an assessment of the current condition of the construction materials and overall structure. The structural engineer evaluates the acceptability of safety levels. And the fourth one, remedial proposals. If the safety levels are found to be unsatisfactory, strengthening work is proposed to meet the required safety levels. Having said that, one of the engineering challenges that we faced during this project was the timing of the site investigations. Because the budget did not allow for any geotechnical and intrusive site investigation before the construction stage, we had to make some assumptions during the design stage, such as the bearing capacity of the soil, compressive strength of the brickwork, and so on. To mitigate the risk of having to change the structural design during the construction stage, we had to provide a conservative design, but at the same time, use our engineering judgment not to over-design the structures to an extent that would have exceeded the budget and led to the cancellation of the project, essentially. Another key aspect of aiming to keep the structural design as lean as possible is understanding the significance of the historic fabric, which can easily be lost when conservation principles are overlooked. Once the main contractor was appointed, the site investigations were instructed and the tender design was adjusted based on these on the site investigation results. As mentioned before, it is extremely important to understand the underlying causes of previous structural failures. However, this is not always straightforward, and some of these will only reveal themselves during the construction stage when more intrusive investigation can be carried out. An example of this on the Crystal Palace subway restoration project was the discovery that the historic drainage behind the retaining walls was in some areas defective and in other areas completely missing. Supporting a new clear span glazed roof. Well, supporting a glazed roof on the existing brickwork came with a few challenges as well. First, the original roof would have been supported on the existing stone corbels, which, given their current condition, could not be used again as load-bearing elements. The solution we proposed was to make use of the generous thickness of the walls and make the roof trusses slightly longer than what the original would have been, such that they bear onto the inner brickwork rather than on the existing corbels. Secondly, as Clive briefly mentioned already, the original roof would have had intermediate supports, namely cast iron columns at mid-span, which were used to break the span and therefore reduce the loads on either end of the roof. Thirdly, as previously mentioned, these walls had bulged out quite badly, therefore applying a significant vertical load on them without strengthening and tying them back could have potentially led to the loss of stability of the wall. Retaining a newly discovered historic landing slab. To the southeast upper steps, as mentioned by Clive, several unexpected elements arose during the excavation required for the proposed works. One of these was the discovery of the lower landing slab, which, although still in its original location, was completely buried under soil and debris. Therefore, we had to revise our design proposal to accommodate this discovery. The initial intention was, as previously mentioned, to rebuild the collapsed wall in RC, reinforced concrete, with a base slab that would support the stonework steps and landing slab. respectively. So when we were asked to find a solution to retain the historic slab in situ, one option we came up with was to rebuild this section of the wall with the heel slab this time, extending as much as the position of the existing temporary sheet piles allowed it. Given the rather significant height of the wall in this location, approximately 4.5 meters, ground anchors would have been required to prop the stem of the wall. Another possible option we proposed was to provide a sheet-piled wall as a permanent structure along the line of the previously proposed RC wall stem. This would have been capped with concrete at the head of the sheet piles, and shear studs would have been welded at a lower level to allow the creation of an RC footing to support the facing brickwork skin. Before making a decision within the design team on whether to implement option 1 or option 2, we looked at the following design considerations. From a technical design perspective, option 1 could have been designed internally by TMP, whereas option 2 was beyond our area of expertise because of the sheet piles and therefore would have required a specialist design. From a health and safety perspective, both options could have been implemented with low risks if adequately planned ahead and by carefully following the agreed methodology of installation. From a sustainability perspective, in terms of main construction materials, we did a quick and indicative calculation of the upfront carbon of the two options for this particular item of work. Our calculations showed that option 2 would have led to a slightly smaller carbon footprint, namely approximately 16% less than option 1. However, this did not take into account the fact that, as this is a relatively small section of the wall, in option 1, some of the carbon footprint resulting from the construction process would be offset by having it built at the same time as the rest of the wall. Therefore, having the entire wall built using the same materials and at the same time translated into a more efficient material transportation to the site. Moreover, option 2, although a bit more sustainable from a carbon footprint perspective, would have involved a high level of noise and vibration to hammer the piles into the ground, potentially creating problems for on-site workers and the adjacent brickwork structures. From a cost perspective, the report provided by the QS showed that option 1 would have been more cost efficient than option 2. So the key points in using option 1 over option 2, starting with the advantages: monolithic with the rest of the wall, therefore better from a structural design perspective. Same construction principles as the rest of the wall, hence more straightforward coordination on site. Designed internally, not by others, therefore more cost and time efficient from a design perspective. More cost-effective construction based on the QS report. And finally, no vibration that could have potentially damaged the existing structure. Also, no vibration meant less noise pollution. And then on the disadvantages side, a carbon footprint increased by approximately 16% compared to option 2. Therefore, looking at the two options from different perspectives and with only a relatively small difference in terms of sustainability, we decided to recommend option 1, bearing in mind that relative to the project as a whole, the sustainability aspect had been well considered and implemented. Sustainable development considerations. The preservation of the historic fabric was a key aspect of our design-making process as structural engineer on this job. I believe that this is not only important from a conservation perspective, but at the same time critical from a sustainable development point of view. For instance, when the works on site started and the facing brick of the north retaining wall were dismantled, we noted that the load-bearing wall behind was not bulging out at the same extent as the facing skin was, most likely thanks to the RC micropiles introduced in 2018. So after carefully inspecting the remaining wall and reviewing all the archive information available, we advised that the wall can be retained provided that we allow for localized strengthening so that only the top section of the wall and the facing skin are to be rebuilt. Within the scale of the project, retaining this rather massive structure had a significant positive impact in terms of waste disposal and carbon emissions. Another example where we applied sustainable principles was when some of the retaining walls had to be replaced or partially rebuilt, and the original made ground backfill had to be replaced with a lightweight material to minimize the pressure generated by the retained soil. Being mindful of both structural, i.e. free draining and lightweight, and the environmental benefits, i.e. type of material used, we specified expanded clay aggregates instead of using, for instance, void formers, which are, of course, far from being environment friendly. Moving on to the as-built proposals, and starting with the east courtyard roof. The as-built glazed roof comprises UB steel sections, upper chords and struts, and a Halfon D10D system as tie rods to keep the bottom chords as slender as possible. As the architectural proposal of the roof was having this partially glazed, we created a finite element method model of the structure to have better control of the structural behavior and also to more accurately predict the global deflection, which of course for glazed structures is a crucial aspect to be considered. To determine the overall deflection in the worst case scenario, we ran a wind analysis of the model under different load combinations and of course different wind directions. Once completed, it became evident that the sectional size of the main structural members had to be dictated by the deflection limit requirement of the glazing system rather than the sectional bending moments and forces capacity. For the trusses to be able to easily accommodate thermal movement without inducing highly concentrated stresses into the masonry, we introduced sliding bearings at one end of the trusses, whilst the other end had been embedded in concrete. To mitigate the risk of corrosion to the embedded steel, we specified waterproof additives to be used in the concrete mix. For the same reason, at the other end of the trusses, we allowed for an RC box formed around the trusses foot using waterproof additives with a precast concrete lid to facilitate future access for inspection and maintenance. We also allowed for air bricks within the RC box facing the roof structure to ensure that enough ventilation is provided and thus keep the trusses foot dry. The east courtyard north and south retaining walls. As already mentioned, the existing north wall has been mainly retained and provided with bed joint reinforcement comprising stainless steel helical bars and also SEM ties to tie back the remaining bulging section of brickwork to the masonry behind. The upper section of the retaining wall was rebuilt in dense blockwork and the facing skin also rebuilt to match the original one. Whereas the south wall was only required localized masonry repairs, as can be seen in this section drawing on the left-hand side. The east lower and upper steps and associated retaining walls. For the south lower and upper steps, we decided to rebuild the collapsed retaining walls in reinforced concrete, again to keep the structure as slender and lightweight as possible. The same principles have been applied, namely the base slab of the RC wall not only mitigates against overturning, but also provides a structural base for the stone steps to sit on. The north upper steps retaining wall partially collapsed at some point in the past to be as least intrusive as possible from a conservation perspective. The collapsed section has been rebuilt as per the original construction, including a small cavity that has the role of breaking the moisture transfer from the load-bearing retaining wall to the facing skin. Ground anchors have also been used here to assist with resisting hydrostatic pressure. And finally, some conclusions. One, pre-construction intrusive site investigations are critical, and if insufficient, can have a domino effect on the overall construction cost and program. Another one would be that a historical desktop study is always a sensible idea. On this particular project, perhaps provisional allowances and solutions could have been thought about in terms of what to do in case the historic slab is found intact. Another one, it is extremely important within the early stages of a project like this to understand the underlying causes of previous structural failures. However, this is not always straightforward. And some of these will only reveal themselves during the construction stage when more intrusive investigation can be carried out. A fourth conclusion, a key aspect of aiming to keep the structural design as lean as possible is understanding the significance and authenticity of the historic fabric, which can easily be lost when conservation principles are overlooked. And finally, it is indeed critical that both the design team and the contractor have the right mindset and pull together in the same direction. Luckily, on the Crystal Palace subway restoration project, we were fortunate enough to be part of a project team where all parties focused on delivering their bit at the highest standard and tackling each obstacle along the way proactively and sensibly. Thank you very much for your attention.
Right. Thanks, Ian and Clive and Cristian. That was absolutely wonderful and really interesting to see just how small the subway was compared to the palace building. I think we've got time for some questions. Does anybody have any questions for any of our speakers?
It's not clear to me who commissioned the building. Was it by the railway company or was it by the Crystal Palace company itself?
Railway company.
Thanks.
Yes, it was the two different stages. And I think the upper station, the lower station was another company.
So the upper station was the London, Chatham and Dover Railway, who were the later arrival to serve the Crystal Palace. London, Brighton and South Coast had got there earlier, and their so-called low-level station. Of course, they have tunnel underneath the whole hill.
I think we ought to recognise that they're in competition with each other.
Oh yes.
You know, there's a new market here. 2 million people a year coming from central London, a lot of them first class, and there's a good market to tap. So if they could pinch them from the other railway station, they did. Good Victorian economics.
And of course, although they were the last to arrive, they did manage to arrive much closer to the subway.
Yeah.
So passengers arriving at the low level station, which is the one that's still there, had to climb up that enormous hill. Fortunately, through a covered way for bad weather, but it wasn't a good competitor really once the new station was in place.
Yeah, just wondering, was there any pushback from the Bromley Council during the planning application process? When it comes to like design or. But question is, was there any pushback from Bromley Council? Bromley Council own the park and the subway. But the planning department might have a different view and during that. And since one of the reasons why Historic England tried very hard and was successful in raising the listing from grade 2 to 2-star, as you'll understand, that means that any application for a planning permission Historic England has to be notified. And so the planning gives Historic England an opportunity to comment on the proposals. You should remember also that Historic England is into this sort of thing, to get things off our HAR register. And we worked very closely with Bromley Council. There was no pushback at all. They were keen and we were keen, but they didn't want to spend any money on it. You have to, and really the project only got going with that amazing grant from the City of London SIP Fund. But it was Bromley who applied for it and pushed hard and politically argued very strongly for it. And we were right behind them. As soon as it was known there was a shortfall,
but there was an opportunity to take up the SIP fund. Then Historic England put up initially £500,000 to match up with the budget. But as you've seen, there were good reasons why costs and time overran. And in the end of the day, we had to find another £600,000. Now that's out of the budget for the London region, which is about 1.25 million per year. Luckily, it was spread over quite a long time. I hope that answers your question.
In fact, Bromley always found it quite difficult to know what to do with the subway and the park, and still does. In fact, there were earlier plans to restore the subway in the 1970s, and they were led in part by a Bromley architect, Ken Catford, who's still around, but he then moved up to work on the Docklands developments in Liverpool. He was the architect there. But we had access. I got photographs taken in the mid-1970s and in the 1980s that I took in the subway, and the amazing thing to me is just how much the grass, the trees and grass and weeds grew, and got back to my own photographs.
Question for Cristian, actually. I like your conclusions there. There's, I think, buried in there are lessons learned, and clearly you struggle to get investigations done early. Just a little trick, I would have called that a tunnel, civil engineering, and then the percentage applied to the cost. You get more money for your investigations, but I can tell you about that later. Did you have to apply any? I mean, it's under the parade road, so it's a highway structure. It's supporting the highway. It looks as though you might have been able to be a bit more pragmatic with the highway standards, because if you apply the highway standards to that, there's all sorts of things that you would need to do, because you're right on the back of that footpath. Was that the case? Could you tell me more about how you had to deal with it, or did you just escape? And if you did just escape, could you please write this up? Because I'd love to use this as a reference.
Yeah, thank you for the question. I did escape it. The short answer is we did escape it, just because both the north and south retaining walls, as mentioned, they had been stabilized back in 2018 by ECOM. And we did not have to interrupt much with the structure that is part supporting the highway. And for this reason, we didn't have to apply for any particular consents or anything like that.
Right. Sounds like you did escape. Where I've been in this situation, the local authority, highway authority, would have to draw up an AIP for repairs to that.
Yes, we've been asked to provide something like this. We were asked to provide something like this, but only if the waterproofing works would have been carried out. But because of lack of finances, unfortunately for the subway, but fortunately for us, we will just deal with this problem when we will have the budget.
Okay, so that makes sense because you are beyond, I suppose, the highway reserve.
Yes.
Yeah. Okay. And I think
yeah. Let's go.
Thanks. Yeah, one of my first involvements was sort of dealing with the Highways Authority in Bromley. I think I hinted at that in my talk. The Highways Authority have a 15 review period of certain structures, and this is one of them. And one of those happened, from memory, in 2016, and that's also put pressure on Bromley to help sort out the problem of the subway. I think there was an additional advantage of the piled pier caps on each side, as well as preventing any further pressure from the retained land behind. It also provided a buttress to the abutment
of the road adjacent to the north and south sides of the subway. And I suspect that was part of their design thinking when they did that.
Cristian, I've got all the language here. You said that the drainage behind the retaining wall had broken down or was missing. What was the original drainage and what do you mean by missing?
Yeah, I think this is a question more for Clive. Hopefully, we as structural engineers did not deal with drainage design. It was a different kind of with drainage, but I think Clive, you can tell more about the existing Victorian drainages.
So one of the things that I didn't have time to talk about was the drainage, which was a mystery pre-contract. There were no records of any drainage anywhere on site. It was not possible to drain the routes out to the main road due to levels. And in the absence of any investigations, we tendered the project on the basis of soakaways to the north and south sides. When we got on site and excavations started, it became obvious that the ground had too much clay in it to be suitable for soakaways. But at more or less the same time as I remember it, the contractor was breaking out the concrete that had been used to infill the courtyard area, for large parts of it, and discovered the Victorian drainage system, which was still more or less intact. We ended up having to line it after a CCTV survey. But it was possible to reuse it, and it actually ran under the vaulted area to an outfall where the rail station once been. And that system collected, as far as we could make out from traces of pipe work, the roof drainage from the cavities of the retaining walls, and also drainage from pipes that were centrally in the columns of the vaulted area. So that really saved us from a very, very difficult problem. So all thanks to the Victorians. But as I said, we never did find out where the Valley Gutter drained to.
Yes, very good question, Matt. These columns, that's the elephant in the room. You know, no one knew that they contained cast iron. Well, they knew they contained cast iron pipes, but no one knew they were drains. And it's already running, I think, of the drawings that ran from courtyard through to the south terrace. They showing clearly on the TV images all the spurs coming in. Every time they passed a column, there's a spur coming in. So that was the final proof that they had been designed as drains for the scuppers of the vaulting.
So I just had a question on the subway structure itself, and looking at the vaulted profile, it looks quite shallow. I was wondering about horizontal thrust on the kind of open edge. Do we have a feeling for if it's tied across, or is it all just working via gravity? If that's something I've thought about at all.
Yeah, we don't have any information in terms of whether there are any ties or not. Again, I think this is something that we will need to investigate once the waterproofing works will be enabled. There are so many unknowns on how the subway was constructed. So yeah, I think it's going to be quite a fascinating project to work on. Hopefully we will.
If I may, I remember the question. You will also the plan that the pillars on the terrace side one over deeper, which is which anyway, they're not the same thickness. I think they're thinner piers on the side of the roof courtyard. Especially north and south, you're buttressed against 2 miles of roadway, so that's all right. Going the other way, and there are cracks indeed along on the west side between the edge of the vaulting and the parapet wall.
Have we got any more questions?
The regular question, these videos, are they produced by historical people?
They're related to the topic.
Right, shall we say thank you again to our speakers